We are Team 22049, and this year we were tasked with developing a point-of-care potassium diagnostic system. This project is sponsored by Dr. Slepian with the Kidney Advanced Project, and our mentor is Dawn McDonald. My name is Vanessa Sobar. I'm team lead and a part of the biomedical engineering program.
My name is Reed Leffler. I'm part of the Biosystems Engineering program, and I'm the team procurement lead.
I'm Prakir Bindra, and I'm part of the ECE program. I'm working on the electrical and software components along with
Teresa Pham, who is also part of the ECE program.
I'm Julia McElwee, and I'm part of the biomedical engineering program.
So this is our poster for Design Day. To start off with some background, kidneys are vital organs involved in the balance of fluids and electrolytes in the body. Potassium intake levels that are too high or too low can have serious consequences on a person's health. For patients with chronic kidney disease, it's the utmost importance to monitor potassium intake. This project presents a portable potassium diagnostic system, which can directly measure potassium content in food or fluid, as well as estimate potassium content through image recognition. While many laboratory-based devices, methods, and testing systems exist, there are no portable systems such as this one for chronic kidney disease patients to precisely monitor their potassium intake. Values of potassium are only guessed by understanding food content from charts or references, and that's why we're developing a first-of-a-kind point-of-care potassium diagnostic system.
Our designed potassium diagnostic system provides a dual approach. It provides a means of rapidly and accurately estimating potassium content of food and fluid through the use of image recognition, as well as directly measuring potassium content in food and fluid through the use of our probe. The key features of our potassium diagnostic system are its portability, ease of use, and accuracy. The components of our system, such as the probe and the Raspberry Pi, are going to be contained within a 3D printed container that is small, lightweight, and compact so that the user can bring it with them wherever they go. This system is very easy to use, and it has two main ways of use. Either this user can directly measure potassium content using the probe subsystem or the image subsystem. Using the probe subsystem simply requires the user to homogenize a sample of food or fluid to be consumed and then measure the content with the probe. By directly measuring the foods or fluids content using the probe, the system can accurately determine a measured amount of potassium content and thus the user's potassium intake. The image recognition system simply requires the user to take a picture of their food or fluid to be consumed. Then an adapted API will allow for image recognition to identify a given food and produce the amount of potassium based on the serving size. Additionally, the potassium diagnostic system has an evolving database that will keep track of the user's potassium intakes throughout the day for each month. This feature helps to enhance the system's long-term accuracy when the user uses the camera image recognition method of the subsystem to estimate the potassium content in food and fluids. All this will be recorded so that healthcare providers can use this information when needed for their patients.
So now I'm going to talk about the software part of our system. It has four main components: the GUI, the communication and processing, the camera code and image processing, and lastly, the internal logs. For the GUI, we use Python tkinter, which is a framework of libraries that allows us to use nice widgets and good layouts for presenting on the user interface. We implemented the software using MVC architecture, which stands for Model, View, and Controller. Model refers to how the data is stored internally in the program. View is what the user sees and interacts with, and Controller is all of the processing that bridges the gap between model and view. Next, we have communication and processing, which would be converting the raw analog data from the probe to usable digital data for the program. The data from the probe is sent to the Raspberry Pi using a USB connection. For the actual conversions and all the math, we are going to use GoDirect libraries, which are a set of libraries provided by the probe company. For camera, we're going to use OpenCV libraries to access the camera from the Raspberry Pi and take pictures. After taking a picture, the next step would be to recognize it, which could be done in two ways: using Google Vision API, which sends the data to Google servers and gets the results back, or using local machine learning algorithms. In this case, we'd be using a program called Yellow. Next, we'd ask the user to input the volume, and then after looking up the potassium content in a table, we'd do some math and display the final intake on the screen. Lastly, we have internal logs. Every measurement taken, either via a probe or a camera, will add an entry to the log table.
Here we have our system block diagram, which incorporates all of our components and all of our interfaces. The most important interfaces we have in our system are between the subsystem and the microcontroller, and the microcontroller and the user interface. Following the probe route, a potassium probe is used to measure potassium concentration on a sample of known volume. This data is sent to the microcontroller via USB or Bluetooth, which is processed through a Python script. The food item and serving size are the input to the system, and a lookup table is used to calculate the total potassium in that serving. This final measurement is then sent to the database, which stores the user's daily intake. This data can be accessed via USB or Wi-Fi by the user or a healthcare provider. On the other hand, if the user doesn't want to use the probe, they can take an image of their food with the camera. This image is sent to the microcontroller and is processed to recognize the type of food. The user can also select the items in a lookup table, and like before, the total potassium content is stored in the user database and can be accessed later.
Initially, preliminary analyses were performed to ensure that our system is lightweight, portable, and able to be used in a variety of environments. We determined that our system weighs no more than 5 pounds, it is less than 300 cubic inches in size, and uses less than 6 watts of power. During our first test, we looked at the accuracy and precision of our probe system. We determined that the probe accuracy is 97.05% and the precision is 3.79 parts per million. These values meet our probe system requirements. During our second test, we looked at the ion selectivity of the probe system. This is to ensure that other ions do not interfere with the accuracy of our probe. During this test, we added various salts to a known potassium solution. When graphing percent error versus mass of the additional salt, we determined that the R-squared is 0.002, meaning that other salts do not interfere with the accuracy of our probe system.
Our device is safe to use and does not pose an immediate risk to the user. In the event that any components are broken, it should be carefully cleaned up and replaced to ensure no damage to the entire system. Our potassium diagnostic system went through many design changes, including 3 different housing assemblies, 2 different potassium probes, and a reevaluation of the volume estimation. Some future directions for this device include utilizing a better potassium probe, developing a smart machine learning algorithm that incorporates volume, composing a database with a larger variety of foods, as well as making the device smaller and more portable. As it stands, the current cost of our potassium diagnostic system is $596, and we'd like to thank Don McDonald and Dr. Marvin Slepian for making this project possible.